I would like to say is, this is the light, so about strongly correlated quantum matter, selected fundamental aspects. But of course I have to say thank you. Thank you. I really have to, I'm really surprised that I got it, but of course it's very nice. And as you know, I was organizing this Congress, and then when I learned very late that I am being considered, because there is a special committee outside of physical society, so I wanted to resign from the committee in order that there is no interference. But of course, our boss, Professor Shirko, says, no way you can resign. So that's how you have now. You have two parcels in one. Okay, so then no good professor or reasonable professor exists without young people, and these are people. I have my pupils. This is Adam Ricesh, who now is head of our department from 1 year, and here is Professor Krzysztof Byczuk, who is professor from Warsaw University, who was also my student, and here is Professor Wójcik, who is professor at Technical University of Technology in Krakow, and here you can see Danka Gocjagło, and some other people you will hear. Maciej Kwidrysiak will give a talk, and our Piotrek Kuterba, who is working very hard during this Congress. And probably there is Andrzej Biborski and Michał Zegronik from AGH. So you can see there are people from all the places where I work in. And I think I should thank, first of all, AGH University of Science and Technology, where I made, after the studies here, the first steps. Then, of course, I moved to abroad, and then I worked and got full professorship at Warsaw University, and now I am here back at the Jagiellonian University. So that's why you have, I have the students, former students, who are now already professors at all those three prestigious places. Plan was originally, how was the plan? Of course, you can ask, because, you know, at least in this country, condensed matter physics and condensed matter theory has a difficult start, more difficult than other disciplines, and I have to say it responsibly, that we have not as easy life ahead as other disciplines, but it seems we are getting appreciated. So I should say why first. Then, what is it? Why fundamental? And of course, I selected examples, but since I have no time, so probably I will cut just in half. About mode localization, what I have done, I built the first thermodynamics of the mode localization. Then about high temperature superconductivity, I will flash one or two results. And then the concepts I have introduced, the spin-dependent masses, and with the help of this concept, you can test the principle of indistinguishability for the first time. And in this indistinguishability principle of quantum mechanical particles, it's a very fundamental principle in quantum physics. And as you know, it has been created here at this university by Professor Ludwig Nathanson. And he was the first president of the Physical Society from 1920 to 1923. So there is another dimension to this research I am doing, and I would like to stress that. And of course, about theory, as you can see, you can use only non-perturbative solutions. And of course, this makes the life even harder. And then you can select the methods, and there is plethora of methods, as you know, in physics, because physics is an approximate theory, not like mathematics. And what is called assumption in mathematics here is called principle, because it must be tested. In mathematics, once you establish it, that's it. I selected certain variational methods. And then, of course, I won't say anything like that about statistically consistent Gutzwiller approximation, but diagrammatic expansion of the variational wave function. I simply do not have time. And what next? And I won't say a word about that. I have to cut that. The first one is quantum criticality, and that's probably in the center of correlated quantum matter physics. That's at the center of this question. Then you have correlation plus topology. That's another very interesting thing, which leads us outside of condensed matter directly to mathematics, some mathematical aspect, mathematical physics. And then, of course, I was thinking of saying few words, but about testing principle of particle indistinguishability. And this is what I'm working on right now, so probably I'll skip it as well. So what is called the correlated matter? Probably I just say a few words, general words, and that's it. And this is the essay I have written to a magazine of the Polish Academy of Sciences some years ago about revolution in the system. And the question is, why revolution? What kinds of states arise when the interaction between particles becomes dominant over the quantum behavior of individual particles in the system? In other words, any perturbation expansion, rho perturbation must fail, and is the concept of particle, of quasi-particle determined? And of course, they may be, of course, where there is a problem, there is opportunity, maybe some instabilities of known states of matter appear, and they are of new type. Then, and that's the first example. The first example is like that it's localized versus delocalized. As you know, when we are undergraduate students, we learn about atomic states, so let's say hydrogen atom, and then, of course, when you go to solid state physics or now condensed matter physics, you will say that those atomic states form a lattice. But when you open the textbook of solid state physics, immediately you start at page 1 with something like that, where there is lattice of ions and almost freely flowing electrons. And of course the question is, why is it so? Are those two pictures, this quantum mechanical atomic picture, complementary to that or not? But if it is complementary, how does the system evolve from one to the other? And one would say, of course, if you have atoms far away, big lattice constant, then you have more or less atomic states slightly seeing each other in a non-direct fashion. But once you start squeezing the system, then the electron orbits starts overlapping, something happens. And this is one of the most violent phase transitions in nature. Here, when you go from here to there, in the case of electrons, you call about insulator to metal, magnetic insulator to metal transition. And for example, conductivity can change in the fraction of a Kelvin by something like 100 million times or even more. So this is a really violent change. Instability of the system. And why is it so? Because apparently the electrons want to move because of uncertainty principle, whereas interaction prevents them from moving. So apparently the one factor compensates the other, and the catastrophe happens. Either everything moves or everything stays, it's blocked up. So that's essentially source of correlated electron physics, which was posed by Sir Neville Mott, and of course many others, studied by many others. So then definition. We have ground state energy per atom, we have atomic energy of individual electron. Now we've talked mainly about electrons, but of course they feel their parent nucleus via atomic energy. Then, of course, you have kinetic energy, either in atoms or the kinetic and transformed into translational motion through the system. Then, of course, every electron feels the attraction from other ions or nuclei. And that's single particle energy, because this is external potential for given electron. And of course, then the last factor is the interaction. And the question is, what happens if the single particle type of dynamics of each electron is compensated by this repulsive interaction of the ion? As simple as that. And then, of course, you have three limits. Because you want to study condensed matter, so you assume that your reference is atomic energy. So electrons circling around atoms, that's our background. And whatever will happen is on the top of it, that's our dynamics. And then, so you have three limits. When single particle energy dominates, then of course you have almost free fermion gas type of limit, because electrons do not care about interaction, or fermions in general, or bosons if they have charge. So it's Fermi gas or Fermi liquid, or in the context of electron, you talk about metallicity, metallic region. Then you have the complementary regime, where the interaction dominates, and that's the most interesting thing, because that's where I said you are beyond these instabilities. New universe of states appears discontinuously, so you have some sort of Mott-insulating, you have high TC superconductors, you have quantum Hall effects, and so on. And then, of course, the question is, where is this critical regime where those two factors, those two energies compensate each other? Because as you know, usually the binding energy in atoms, this single particle is negative, or repulsive energy is positive, because it's mainly Coulomb interaction, let's say in non-relativistic system, so therefore they compensate each other. So then, is it seen, these limits? First of all, you have, for example, you take liquid helium-3, and it's canonical Fermi liquid. What does it mean? If you measure distribution, momentum distribution of atoms, whole atoms are regarded in liquid as quantum particles, so it's real condensed matter, liquid helium-3, normal phase. So it's very difficult. It's by neutron scattering, you can directly measure the Fermi-Dirac distribution of atom momenta versus energy. And this has been done only in 1955 by Mook. But then, if you have beautiful Fermi-Dirac distribution for the gas, even though it's a liquid, with the Fermi energy, at given energy, at given temperature, it's fixed. But then it turns out you have to adjust the mass of the liquid atoms, even though liquid helium-3 atoms, liquid helium is very light liquid. It's less than 1/10 of the density is less than 1/10 of the density of water. So you can see that the masses, this is the specific heat, but these masses are something like 4 times or 6 times as heavy as they would be if you weighted the atom in the vacuum. And then when you squeeze the liquids are generally difficult to squeeze, but liquid helium you can squeeze relatively easily because it's a quantum liquid. So they are very strong quantum zero-point motion, so you can squeeze the zero-point motion, and then everything destabilizes and you have quantum solids. So you can see it even in the interacting system. One of my students, now professor, becoming in the matter of weeks, Adam Rycerz, in his PhD thesis, calculated exactly. I have invented a method called exact diagonalization plus ab initio approach, and you say you take a ring of 12, 14, 16, 18 hydrogen atoms and squeeze the ring. You can solve it exactly, even readjust single particle wave function to the interacting state. They are strongly renormalized, but the renormalization is finite. And you can see if you have, let's say, 14 atoms, and if this distance between atoms is more than 2 Bohr radii, then you can more or less Fermi-Dirac distribution. Again, of course, here is a positive momenta, here are negative momenta. Here you have only see the half of the other what we for negative momenta. But when the atoms increase, the distance between atoms is increased, it's smeared out. So this Fermi-Dirac distribution, this Fermi surface existence is destroyed. And that's essentially, even in finite systems, there is no discontinuities because the system, finite system cannot have phase transition, but you observe that. So what happens? If this mass is renormalized, so this means that the Fermi energy, the energy of the highest occupied state, which is inversely proportional to the mass, is going to 0. So does it mean that the Fermi sphere reduces to the point when mass is infinite? No, because that would violate Heisenberg principle. But then different is phase transition, new universe appears, and lattice of something like that is created. So the system avoids the singularity and creates this thing. Okay, so I probably, and then of course you can study the, study the situation. Okay, Peter agreed that I can take 5 minutes, so I have 10 minutes. If Peter agrees, okay. So anyway, if you calculate the thermodynamics of this system, it turns out you have a beautiful border. Here is temperature, here is magnitude of interaction relative to single particle energy. There is a beautiful border between those two systems, and you have critical point. And I have predicted in 1987, this critical point. It was here in this paper, and it was experimentally beautifully confirmed in 2003, 2004, 2005, in a series in the best journals. Then you can see here also an example of metal-insulated transition for somebody not working in solid-state physics. It's a crazy system, but anyway, the system has been chosen properly. Here you have in logarithmic scale resistivity versus 1/T. So you can see here they are high temperature, here low temperature. Here you have semiconductor, and here this 100 million times resistivity bungs. Then it goes, as you increase temperature, it goes more or less flat, bad metal, bad metal, and then goes back again to quasi-insulated event. All this can be explained. All this can be explained. Okay, so then there is, so that was the thing, and of course there were a series of papers and reviews and so on. Why superconductivity? As you know, Pierce Coleman made me think, and with Danka Godziagło, we have completed the chart which started with Pierce Coleman, and you can see that you observe superconductivity or superfluidity in all energy scales, starting from early universe, or maybe in quark-gluon plasma, it gets discovered up to these atomic condensates and superfluids. So this is a really universal thing. And what was the idea? And now I will say, and then to the results. The idea was that, and this was idea, I have derived a model with my colleagues here in Sweden. I have derived the exchange for those correlated systems. It's essentially Heisenberg exchange model with anti-ferromagnetic interaction, which means this coupling constant, exchange constant is positive. But the full exchange, if you have moving fermions, is not just a scalar product of the spins, but also something density correlation. And if you introduce explicitly the pairing, singlet pairing operators, surprise, surprise, you can rewrite exactly in the, not Cooper pairs, but in the pair language with attractive interaction. And that was essentially the idea which I have got. I worked then at Purdue, when I got it from Phil Anderson. And then, of course, he said that in our model there is not only magnetism, but also superconductivity. And then, of course, I extended it to various systems. And eventually, the theory landed, the new start was in 2017 with now almost guy who finishes habilitation with Michał Zagrodnik and Jan Kaczmarczyk. We extended it from TJ model to some sort of extended model with this strong local Coulomb interaction, which is called Hubbard interaction. And then what you get, and we got beautiful comparison. First, the mean field type of approach. We got the superconducting phase. This is the phase diagram for high TC systems. This is the phase diagram for high TC systems. And here is temperature, here is doping, since the electrons are strongly correlated, so they can move only from the insulating phase when you kick out some electrons, so there are free places, so the electrons, we say holes, can move. And the superconductivity in those systems appears and disappears. And that also was a big puzzle. And within this our approach, whatever we do, whatever type of parameters we take, there is always upper critical concentration for disappearance for disappearance of the superconductivity, and that can be explained, but of course nothing is ever easy. It turns out that the simple phase diagram is very complicated, contains some charge order and so on. And here is the habilitation of Michał Zagrodnik. He noticed that below the so-called optimal doping, you observe a plethora of different instabilities as phases, and phases, I don't have even time to explain it, sorry for that. And then you observe pure superconducting phase like that. So this is, let's say, qualitative, maybe not yet semi-quantitative phase diagram, but of course other properties can be calculated quantitatively. It turns out that in those systems there are two energy scales. One is very low energy scale. Here is energy with respect to the Fermi energy. Here is momentum with respect to momentum, Fermi momentum. So at low energy, close to Fermi surface, Landau-like quasi-particles. And then deeper, there is a kink. And deeper, there is another, as if another sort of particles appeared. And this was the method, new method, which was invented by Maciek Fidrysiak just, as you can see, 2 years ago. We can get even probably almost fully quantitative comparison with the experiment of the dispersion relation for the quasi-particles in the superconducting phase. Okay, I have no time to talk about mechanism of that. I have to finish in 1 minute. And so there is an extension, because if you say that exchange interaction plus correlations are responsible for pairing, local pairing, that those pairs move in real space. So therefore, where are those magnetic fluctuations? They are in the background, even though Cooper pairs are singlet operators, but when you excite them, then spin degrees from the singlet state should be shown. And these are results not yet published, complete results from different weeks. And you can, these are, of course, again, parameters. And this is 1/n expansion from this, our statistically consistent Gutzwiller method. So this is directly field theoretical methods applied here. And you can see that the beautifully agreed spin fluctuation or spin wave mode with experiment. And there are another modes which we cannot identify. And even if the system is strongly doped, there are 11% of holes, you observe that there's still the spin fluctuation, and you observe charge fluctuation. And it seems that this our type of approach, this new type of approach, we will be working on that in the next year or two, that's this new type of approach works very well. Oh, sorry, I cannot be able to show outlook. Sorry for that. Strong correlation, we should call it strong interactions, but strong interactions are reserved for elementary particle physics, so we call it rather about strong correlation. By strong interaction, we mean that the interaction is much stronger than the single particle energy, leads to high TC superconductive and spin-dependent masses, where we can address nicely the question of distinguishability versus indistinguishability for quantum particles, not just coming from quantum to classical, but those two types of states from in the quantum states. Then, of course, selected properties of high TC and related superconducting systems are described in a semi-quantitative manner. We are now preparing big review articles to physics reports. Hopefully, it will be finished shortly and published early in 2020. And then the situation with spin-dependent heavy masses, we have transmutation of indistinguishable into indistinguishable particles. It turns out, and back, as you polarize the system more and more, first the system is unpolarized, the masses are equal, and the Fermi-Dirac or corrected Fermi-Dirac distributions are easily calculated. Then they are becoming distinct. Two liquids like electron and proton, they have different masses. Of course, they have also different charge, but you can see that they are distinct. And then once you saturate the system, one spin state disappears, and these one spin saturated electrons again form the indistinguishable liquid. We shall see what will come out of that, okay, as a function of applied field. Thank you very much. Sorry for such a sketchy talk.